people out of how many, 40. If in the next 5 minutes no more people show up, then I will give you the slides and basically finish today's lecture. I'm sorry. This is the time to come to have the lecture, to have an interaction. I want to be interactive. I want to have some sense of discipline. I'm doing it again. I'm not doing it because I have to. I'm doing it just a great courtesy to Sergey Gelevich. I'm extremely busy. My wife is complaining that I'm not spending time with her. I'm having trouble with that. And then I'm sitting here and there are only 5 people and I'm really, really annoyed. Let's start. Thank you for coming, those people who came. So today we will consider high-level forecasting problem, and we specifically will focus on a parametric forecasting problem. Let me give some motivation, and then I'm going to go into the details. So today's lecture is based on chapter 3. I think this is the most difficult chapter of the book. So it takes some time to understand it. And I personally don't necessarily agree how they structure the material, how they present the material. I have my own view on how to explain these things. So if you go to the original book, you will see that it's explained a bit differently from what I explained. But the gist of it is the same, of course. So we will be, in this lecture, we will be focusing on construction of optimal point forecasts. That is, we just have a data Z, and we want to give the best possible prediction of outcome Y. The alternative is predictive density. Predictive density is when we come up with the whole distribution of outcomes with assigned probabilities. And the predictive density naturally arises under the Bayesian approach, which we will consider towards the end of the lecture. And of course, a point forecast is just some feature of the predictive distribution. If we know whole distribution of y's, then of course we can use it to construct a point forecast. So in that sense, generating a predictive distribution is a harder problem. And the most important concept here would be the concept of risk, which we are going to introduce very quickly, like on slides 3 or 4, which will be the focus of everything evolves around risk. So in the previous lecture 2 weeks ago, we considered a loss function, which was the fundamental building block for the risk, which will be the fundamental building block for the risk. Now, as I said, for the motivation, we will be focusing on a parametric forecasting problem, and the distinct feature of a parametric forecasting problem is that it's fully specified up to a finite dimensional unknown vector, which means that we assume some model of the data, of the forecast, of anything. And so we say that we know them up to some set of unknown parameters, and our goal is to somehow recover the parameters from the data and then use the recovered parameters in our model to come up with the forecast. An alternative to this is a non-parametric approach, where we deal with an infinite dimensional set of unknown parameters. Basically, we describe our data generating process, our forecasting rule, in terms of some functions, not parametrized. And then somewhere in between, there is the semi-parametric approach, where we can specify some objects of our forecasting problem in terms of unknown functions, and other objects in terms of unknown parameters. So this is all intuitive, I guess, and for the most part of this course, we will be focusing on parametric forecasting. If time allows, we will touch upon not semi-parametric, non-parametric, but really non-parametric estimation is its own subject area, and it really needs usually like a whole class on non-parametric methods. And for us, lots of ideas that we want to learn can be learned by considering parametric forecasting models. Okay, so we start with classical approach to forecasting, then we will use this we'll go through all kinds of issues with the classical approach to forecasting, and then we will consider different facets of this classical approach to forecasting, like interpretation of forecast optimality, risk in the information set, minimax, and average risk. And then we will consider an alternative approach to forecasting, which is a Bayesian forecasting. And then we will contrast them. So let's start. Let us begin with the setup and fixing the notation. I introduced some notation in the previous lecture, so let me repeat, and maybe relative to the previous lecture, it's a bit more precise. So our forecasting objective is to predict y given z. Y may be a vector or could be a univariate, so we can be predicting a scalar variable, or we can be predicting a univariate, a vector of variables. Z is some information, or not information, sorry, some data, which we denote as all data in our this is all data in our sample. And you can think about this T as a cross-sectional collection of data points, or as a sequential collection of data points. So T can be interpreted as the number of observations in cross-section, or as the time in a sequence of observations when we are making a forecast. What is the big difference between cross-section and time series sequential data? The big difference is the dependence. If the data are arriving independently from the previous observations, then we are in effect in a cross-sectional setup. While if there is a dependence in the arrival of the data from period to period, then we are dealing with time series. If we are in the time series context or cross-sectional context, doesn't matter. We usually include into Z past values of Y and possibly useful variables xt. So our ZT is this whole set of observations that we have at time t. For example, then a usual example would be where Z doesn't include any X, but includes only Y, would be autoregressive processes, autoregressive integrated moving average, ARIMA, or vector autoregressive forecasts. Then we wrap everything we know up to time t into the information set. And formally, probably you know it from your probability class or econometrics class, this information set is the sigma algebra generated by ZT. But it's not that important for us. Formally, this is what it is. And if you know it, great, then it can ring the bell. If you don't know it, fine. We are not going to use this terminology much. It's just to set the formality. Then we assume that there is some joint distribution of Y and Z, which we call the data generating process or the true model. In reality, of course, we usually don't know it. We just observe some data and we don't know where it's coming from, or maybe we don't know the precise model, or even if we know the precise model, we don't know the parameters. So we just write it as some joint distribution that has probability density function written like so. So can be also written like QYZ YZ theta, which is equivalent. And then theta is the set of parameters of the joint distribution. And this is where our parameterization, one place where parameterization comes in. So we are dealing with a parametric forecasting problem, and one place where we impose parameterization, we assume that usually we assume some functional form for this guy, this object, and we say that we know the functional form, but we don't know the parameter. We assume that, sorry, the functional form, but we don't know the parameters, and we use the data to learn the parameters. Now, we restrict, as I said, we restrict attention to point forecasts, which we denote by F, which are the functions or functions of the available data at the time the forecast is made. And the available data is Z, or Z small. We, throughout this lecture and everything that follows, we follow the standard convention by using capital uppercase letters to denote random variables and lowercase letters to denote realizations of the random variables. Also, I will repeat it maybe several times. Keep in mind and don't forget each time on each slide, keep in mind that when we talk about Z capital or Z lowercase, we are dealing with the whole history of data, the whole data set that is available to us. So it's not just, say, if we think about a cross-sectional setup and like we have observations on, say, a person, it's his or her income and all kinds of characteristics, job experience, education, and so on, then Z would be the whole data set containing all people. And then Y will be a new person, like Y capital or Y lowercase. It is a new person that arrives, and for which we don't know the outcome, but we know, say, it's observation, Z at t plus 1. And then we want to construct a forecast of using this Z, which is the whole data set, then ZT plus 1, and to arrive for the forecast of that person income to YT plus 1. So how exactly, now I'm talking about this bullet point, how exactly we will, and this is supposed to be our mapping F, how exactly we map this available data to the outcome depends on a set of unknown parameters theta, which we need to estimate from the data. And which means that if we know these parameters, excellent, but usually we don't know. I guess in practical applications, we never know the parameters. We need to estimate them. And since everything we have is the data, a Z, then ultimately the estimate of these parameters is also a function of Z, so of the whole data set. So ultimately, everything is the function of the parameters. Oh, sorry, function of the data. But nevertheless, sometimes we will be just writing FZ, which emphasizes the fact that ultimately everything is the function of the data. But sometimes, or maybe even for during this lecture, we will be writing FZ theta. This is to emphasize that we can construct some rule up to a set of parameters, and then later we might estimate the parameters separately. There are reasons to do this distinction, which I hope will be clear as we proceed. And then finally, we will be employing some loss function when constructing a forecast. And the previous lecture hopefully gave you an idea that you can choose from a variety of loss functions, and you should be choosing loss functions based on your subject area. Today, we are not going to think or talk about choosing loss functions, I hope to give you some assignments that show differences of when it matters to have different loss functions. Today, we will consider either the general loss function L or some examples with different loss functions, like squared loss, linear, or ln x. Now, this part of the lecture is about the classical approach to forecasting, which is also a frequentist approach to forecasting. In this approach, I'm not talking about, for now, I'm not going to explain some deep philosophical or conceptual divide between classical slash frequentist versus Bayesian approach. I will postpone it till later today, but I will come to it. Once I start talking about Bayesian approach, I will talk a little bit about the philosophical distinction between classical frequentist versus Bayesian approach. But right now, it's better to focus on just one approach, understand it well, and then see how it can be done differently. So if you look at this little mapping that I showed, observe that I'm a little bit not careful here, because there is data Z that we use to construct the forecast rule. Sorry, to construct the forecast rule, which this data Z usually, as I said, includes the whole sample of Y's and X through obtained up to time t. And then that data set Z results in the forecasting rule Fz, which we then use to construct a mapping rule from Zt plus Tt plus 1 Yt. Yt plus 1, sorry. I need to, let me write it here. So we use this forecasting rule to map Zt plus 1 into Yt plus 1. And in that sense, we are constructing a decision rule. We need to decide, given the data Z and the new observation Zt plus 1, what will be what action should we take, or what should be the outcome. So we can interpret what we are doing either in terms of actions or in terms of outcomes. Why I'm saying this is just in the action interpretation often occurs in this literature, so you might see it later. So that's why sometimes Fz is called a decision rule. Now, in the classical approach, a good forecasting model minimizes so-called average loss or risk, where risk is defined literally as the expectation of loss across all data sets and across all Y's. several comments are in order. I'm emphasizing again that data is the whole set of observations. So when we are computing this integral, we are computing it across different samples coming from the data. This is, I guess, an inherent feature of the frequentist approach, where the world is viewed that there is some true data generating process, and what we observe is a sample from that data generating process. And our forecast rule should be good across different realizations of that sample. So I said, usually we don't know this distribution, the data generating process. I said this already. So that's why I will keep denoting, marking it by red for a while, then I will drop that. And then observe that here to emphasize that we are dealing with some fixed decision rule that is a function of the data and some parameters. We write our average loss or risk as dependent on that decision rule and on the parameters. What that means? What this means? This means that our decision rule should take our data set and spit in the as a input and spit out a forecast. If we have a different realization of the data set, supposedly our decision rule, not supposedly, our decision rule doesn't change. There's a function of this data set. Of course, it will spit out a different outcome if we get a different input, but as a decision rule, it's fixed. Then what we want to do with this guy, with R, we want to minimize it with respect to F. We want to find the best decision rule that minimizes the risk. Then it is sufficient, since all that we have in our observations is the one sample Z, then the classical approach is usually focusing on this internal integral and constructs decision rule F based on just this internal integral, and that decision rule is, of course, will depend on Z. So there is a subtle difference here. It's like ideally we want to minimize this object. Where F is a function of the data sets, but we are dealing with just one data set in practice, which means that all we can do is to focus on this integral. And so that's why the classical approach usually quickly, like from this formulation, it goes to the formulation of minimizing this object with respect to F. And you will see how that differs in the Bayesian approach. So for the time being, we will be focusing on this guy, minimizing this object. And then later we will go back to this more like a bigger minimization problem. So there are two approaches how we can minimize this thing with respect to the F decision rule. One is very straightforward, it is called a sample analog approach. We choose some parametric model for the forecast, like GZT beta, where beta are parameters. And then we write the sample analog of the above integral, which means if this is an integral, then the sample analog of this integral is the sum, average loss function across the observations. Then we minimize this object with respect to parameters beta, and the resulting minimizer is beta star. And then since beta depends, this beta star is the vector of parameters depend on z and theta. The z is our data set, theta is our parameter of the joint distribution, which we don't know. And we don't directly estimate it here. The forecast, but nevertheless, the forecast decision rule logically or conceptually depends on z and theta. And so we can write that if our forecast decision rule, given our data and parameter theta is this, where zt plus 1 is the observation that the new observation that we base our forecast on for the outcome. And so, for example, a simple example of this would be least squares, quadratic loss function, a linear least squares with a quadratic loss function. So we can write zt, say, prime beta squared, and we minimize it with respect to beta. And that results in the usual formula for the OLS. So this seems, and then you write any, so here we make two assumptions. One assumption is about the loss, that it's quadratic. Another assumption is about the parametric model for the decision rule G. And this might seem super intuitive and easy. You just choose any parametric model that you think is the appropriate model. You choose any loss function that you think is the appropriate loss function, and you go with it. And as a matter of fact, this is how a lot of the estimation can be done. But there is an issue with this approach. So this can work beautifully. Everything is great, but there is an issue. Can anyone tell me what can be the issue with this approach?
It's like the problem of choosing the model itself. Like we don't know, we can only assume, and if our assumption is wrong, well, that's not a good way of forecasting.
Yeah, so that's right. That's one thing that quickly comes to mind. But remember, during the practice tutorial on Saturday, I said that, well, we can always divide the sample into two parts, use one part of the sample to estimate the model, and the other part of the sample evaluate the model, and then compare across different models on the test set, and then choose the one. So we can then experiment with different models and choose the one. So this is perhaps not a bigger issue. It is an issue because ultimately the model selection is a big issue, and by doing the sample analog approach, we are restricting ourselves in the model selection procedures. But where does this restriction come from? So let me repeat. It's potentially we can use the sample analog approach to do model selection by dividing our set into training and test, and then evaluating the training models on the train set, and evaluating them in the test set, and then comparing the evaluation outcomes. But this can be restrictive. Why?
Maybe we do not always have a sample analog to any model.
You see, I think we can always write it this way. So the way I formulated the problem, like minimize this expected value, that's it. We don't need to do much. We just choose the loss function, quadratic, linex, I don't know, exponential, you name it. And then we choose the model. And then we go ahead. So it seems like it always works. It seems like it always works. Okay, the caveat is that if we want to do if we want to come up with any sense of the precision of our forecast, and we want to see some errors, that's restrictive because we don't know how to. So there is this object, which is an expected loss, and there is this object, which is a sample analog. And there can be a disconnect between them. For example, it can happen that the expected loss just doesn't exist in the population. It just blows up. While this object always exists because we always deal with finite samples. That is the first. And then how should we think about what we are doing here? So it's a bit of an issue. Another issue is about the restrictiveness of the model selection procedures. Some of the model selection procedures are relying on information criteria or some statistical theory, which requires knowing the statistical, what's that? Okay, which requires knowing statistical properties of this object and this object in order to then make the selection. And this sample analog, and ultimately knowing these properties relies on some assumptions about this. And then checking if these assumptions hold in the data. And here we kind of sidestep all of these issues. We totally ignore them. We formulate it as a sum, minimize. And if we want to do some statistical analysis of like errors or the quality of our model, like using archaic information criterion or Bayesian information criterion, or any other information criterion, or R-squared adjusted or anything else, we need to deal with this, go back to this object and understand it and deal with this. And how our estimate behaves in the population. And how it changes as T changes. Okay, so that's about the sample analog approach, but potentially it can always be used. And in many contexts, it's actually you're doing it without even thinking about it. Now, there is an alternative which is more widely used. And I would say that usually when you learn about model estimation, you often learn it through the lens of the two-step or so-called plug-in approach. And the difference is that we don't go to the sample analog. We deal with that expectation object, with the expected loss. We choose some family of models, suppose the linear models or quadratic models or exponential, some family of models. And in this family of models, and in our case, it will be a parametrized family of models. And in this family of models, we we solve this problem of minimizing this expected loss with respect to f. And the difference is that the resulting solution will ultimately depend on this unknown data generating process. And I will show how it works in the coming slides. And then in the second step, we, instead of solving this problem, so this is our first step, we then go and estimate a feature of the distribution that is needed to construct the decision rule. Now, let me give you examples of this. So let's say we have a mean squared error loss. So our expected loss is going to be this. Then we can do the usual trick that perhaps you've done before. We add and subtract the expected value of y. Then we combine the terms and open the square root, oh, not square root, the square function. And we have the quadratic term, this quadratic term, this quadratic term, and then the interaction term, which will be integral of y to y minus expected value minus f py dy. And this object is going to be 0. Why? Because we can take this out of the integral sign, and then integrating this over this is 0, because it's just this e part doesn't depend on y, and integral of y over py is e. So the whole thing turns to 0. And then we are left only with the two quadratic terms. The first quadratic term, is by the definition the variance of y, and it doesn't depend on f. So when we're minimizing this guy with respect to f, this part is irrelevant. While the second term is always non-negative, and so the best we can achieve is turn it to 0. If we don't turn it to 0, then we are not minimizing it, the whole thing. So that gives us that the optimal decision rule is an average, is an expectation of y, given the data z. Now let us go back. That is our first step. So this is the step where we minimized this guy for a specific loss function without even knowing this. We still didn't know this, and we didn't make any assumptions. The only assumption that we made, we assumed that the loss function is quadratic. And that allowed us to derive the first step, the optimal decision rule in a population. Two notes I know, two observations I know. One observation is that suppose we know this parameter theta, suppose we are in some ideal world or some ideal situation where we know this object, this data generating process. Then observe that still our optimal forecast is the mean value of y. And that means that when the new value of y arrives, we are most likely to miss it. Because if y is distributed continuously, we would never get a precise estimate of y. Moreover, sometimes we can be very far with some non-zero probability, but maybe with some or we might never hit any of the y's. Imagine that y's appear -1 and 1 with probability. So suppose we are dealing with a discrete distribution and y's appear either -1 or 1 with equal probability, and we know that, then according to the quadratic laws, our optimal forecast will be 0. And so we never hit y. That teaches you a lesson that when you're constructing a forecast, you are not forecasting the next value of y. You're not necessarily forecasting a next value of y. You're forecasting some function of the distribution of y. Here is the mean. And it can be never any of the outcomes, as in this example. But on average, we will be close to y. So another lesson that you learn from this is that if your objective is to really hit y, if you want to be you want to nail y, so you want to say next period it's -1 or 1, and that's your decision, then you need to consider some different loss function. quadratic loss function doesn't work. And of course, the second observation here is that in reality, we don't know this object. We don't know this guy. And that's where the second step comes in this two-step approach. Now, as we estimated the optimal decision rule in the population, we need to somehow estimate it given the data. Any questions about this so far?
About 1 and -1, so why doesn't our MSC work? It like kills the minus or something? Or I misunderstood it.
So sorry?
About -1 and 1, why?
Yeah. So what's the question?
So does it work with our MSE loss function or not? I misunderstood it.
So it does and it doesn't. It depends. That's the point. It depends on what you want to achieve. Suppose you're flipping a coin and you're using a quadratic loss function. And you want to predict, given the set of observations, suppose it's a stupid trivial situation which you never do, but imagine that you're in this stupid trivial situation that you're observing a set of flipped coins, which -1 is heads, 1 is tails. So you observe heads and tails, and then you know that they appear with probability 1/2, and then you're asked to predict the next value. If you are minimizing quadratic loss in constructing your forecast of the next value, then your prediction would be 0. So you say neither heads nor tails, if this prediction is allowed, which tells you that the quadratic loss in this situation might not be appropriate. Because ultimately you're asked to predict -1 and 1, or 1, -1 or 1. This example has, I just gave it as a trivial example, but it has a broader implication that your goal when you're choosing to minimize a loss function, and in this example, a quadratic loss, you are arriving at the decision rule, which is the average expected value of y, which is a feature of the distribution py conditional z theta, and but not exactly y. And it can be, in a particular instance, it can be very different from y. And that's all I was going to say. If you want to think about practical applications or practical consequences of that, suppose that you are in a central bank and your task is to predict next quarter inflation. And suppose you make a prediction and you miss it. The point is that even in theory, and suppose you're using a quadratic loss to predict the inflation, then even in theory, you never predict the exact inflation next period. What you're doing with the quadratic loss, you're predicting an average inflation. And so on average, if you will be repeating your forecasts for like 100 years, or 10 years, then on average, your forecast would be hitting the average value of y, but not necessarily y itself. which means that in some period you would never, like in the case of again with the inflation, you in some periods you can be predicting too much, in other quarters you might be predicting too little, and it's okay as long as on average you predict like on average you predict well. Does this make sense?
Yes, it does. Totally. Thank you.
Yeah, you're welcome. And we will talk about these issues of forecasting. Overall, I think it's important to emphasize. This is why I like this book by Timmerman, Elliott and Timmerman, because this is a unique feature of this book that it emphasizes. There are many books on economic forecasting, and there is whole discipline called economic forecasting. There are like conferences on economic forecasting. There is a journal of economic forecasting, a journal of forecasting. But I think so. There are tons of resources, and it's a unique feature of this book by Elliott and Timmerman, who go into these conceptual issues, and they help to think about the right way of how you should think about your forecast and what it does. Not so many books or papers are achieving that. Anyway, let us move on. Now, we derived this optimal forecast using this trick of adding and subtracting, but there is a more general approach to solving this problem. There is a more general approach to solving this problem, and the more general approach is just calculating the first order condition. So differentiate under the sign of the integral, and then try to solve the problem. So let's see how it works in the case of the MSE loss. And then we will think a bit more about, just a little bit about the general case. So we can just differentiate this expected loss. We bring this under the sign of the integral. Basically, that means that we need to calculate expected differentiated loss and assign to 0, assuming that it's so we are minimizing that it's a convex function. Then say if we have an MSE loss, then the derivative of the quadratic loss with respect to f will be this. Then we can substitute it here. And so from here we get 0 is equal to this, which implies the same as what we got before. And this approach is more general. You can apply it to more loss functions than this trick with adding and subtracting. But this trick with adding and subtracting is useful for other purposes, and we will talk about it. I mean, we will see that trick in other contexts. Let us use this differentiating. So here's where it's useful. The differentiation approach is with lean loss, which is, we had this example in the first lecture. We have the sum of positive error with weight alpha and negative error with weight 1 minus alpha. And here 1 is the indicator function, and alpha is between 0 and 1, and alpha, it's a parameter of our loss function. We just fix it. So then the expected loss, we can write it, just substitute this loss function here, write these integrals, then we need to differentiate it with respect to f of z. Differentiating it with respect to f of z, we need to differentiate here and here. So we apply the Leibniz rule, the usual thing, probably you learned from in calculus. Then this differentiation, you can check it yourself, results in this rule very straightforwardly. I mean, in this condition, where py conditional on z is defined as this, is basically the mass of y's up to x. So solving this, we can solve it for pyzfz. That gives us this. Let me erase it. So you can just simply solve it for here, bringing to one part, and what's left is alpha on the other side. So we get this from here, and then we can just invert it and get this as a solution for the optimal rule, where p minus this guy is the quantile function of y given z. So alpha is the quantile, like 0.1 would mean the 0.1's quantile. And then this is the value of the distribution at 0.1 quantile, or alpha's quantile. Now, let us look at an example with, say, which we never know, but just for the sake of an example, let us consider, suppose we know this guy, this object, and suppose it's just normal distribution 0, 1. 0 mean 1 variance 1, just to see how it works. Of course, in reality, again, I emphasize for the 100th time, we never know this, but just for an example. Then, depending on alpha, that would be the percentile. How we calculate this? I calculated it myself. If you have the book, in the book, the picture is wrong. So I calculated it myself. And you can calculate it yourself as well, very easy. In the book, they flip the picture, if you have the book. It's if normal distribution is 0, 1, so this is normal density of the normal distribution, and say the percentile, if we want say 0.2 mass, then that would be the percentile approximately -1. So that's how I calculate. And 0.8, say here. Sorry. If we go to 0.8, so the shaded area is 0.8, then it's quantile is 1, so it's this. Now, but of course, just I'm explaining how I constructed this figure. The point why I'm showing this figure, just to give you an intuition what a different loss. So far we saw a quadratic loss function. Now we are looking at the decision rule associated with a lean loss function, a different loss function. And that different loss function is parameterized by alpha. And it's our choice, which choice of alpha we make when we construct the forecast. And by the way, just jumping ahead the gun, alpha is a parameter of the loss function. It's not a parameter of the data generating process or model, which means that which means it's kind of a higher level parameter. We can choose it based on the subject, the problem, or we can also estimate it. And alpha is called, because it's a higher level parameter, very often it's called a hyperparameter. And so it also can be estimated. Suppose we can be choosing not only models, we also can be optimizing forecast across different loss functions or classes of loss functions. It depends on what we want to achieve. Anyway, but suppose we don't want to estimate alpha, but we want to just fix it based on some logic. Then if we fix alpha equal to 0.5, then we have the symmetric loss, and our prediction is 0, which is the median value. And you can, basically that would be just by the definition, the median value of any distribution, it's 0.5 quantile. So the median value of normal 0, 1 is 0. Then if alpha is small, like closer to 0, 0.2, say, then what that means? So that means that we will be forecasting like with normal distribution, we will be forecasting negative values. So alpha equal to alpha closer to 0 means that we impose large penalties on negative forecast errors. So negative error is bad for us, and that's why we predict closer to the negative part. And in reverse, if alpha is closer to 1 from 0.5, then we will be biasing our forecast towards positive values of star, which means that this is because with this kind of loss function, we put higher values on positive errors. So this is just to give you, this closes this example, and this was just to give you an idea how we impose the different loss function and we get a very different decision rule. And there is one more example, which we will be using later. That's why I'm providing it here. This will be an interesting example, and it will be useful when we will be comparing classical approach to the Bayesian approach. So we will be using this loss function for examples that come later. So that's why I'm providing it here. Sorry, one thing that I wanted to mention about this lean loss is that obviously this is related to quantile regressions. If you heard about quantile regressions or ever encountered them in your econometrics class, lean loss is the loss that generates estimates for the quantile regressions. In particular, when alpha is equal to 0.5, we have a median value as our prediction. But overall, by choosing alpha, we can trace the quantiles of the distribution. So that I wanted to mention. That's why this example is important. And then with Linux loss, let us go through it. So in this case, the loss function is given like so. A is a parameter not equal to 0. Then we can write the we again can put this here. Then you can calculate so that this loss function, it will be like integral over exponent a e py dy minus a integral e py dy and minus py dy. This is 1. E is equal to it's an error, so it's y minus f z. So then integration of this with respect to py would give average value of y, so this guy, and then fz doesn't depend on py, then the whole integral will turn into 1, so we get this term, and similarly substitute y minus fz here, and then we get this term, where myz is a moment generating function for this object. I mean, for this object, which we assume exists. So here at this point, we just substituted expected loss, or substituted Linux loss into this expected loss integral, and this is what we got. Now, calculating the derivative of this object with respect to fz, so it's very easy. So like this term, if we differentiate with respect to fz, would give us minus a exponent minus a fz m, and differentiating this with respect to fz would give us a, because this doesn't depend on f and this doesn't depend on f. Then a would, if we equate it to 0, a would cancel out, and we get this equation as a optimality condition. Then taking logarithms from the both sides and solving for f star z, we get this solution. Observe that it is very different from the previous two examples. And yeah, let me see. Right. So different loss functions result in different solutions for the optimal decision rule. But observe that one thing that I emphasized from the very beginning. In all these three examples, the optimal decision rule is a function of the data generating process Py. So if you go to the quadratic laws, the optimal decision rule is the mean value of y, which is a function of the data generating process. Here it's a quantile, which is a quantile of the data generating process. Here it is this slightly complicated object, but still a function of the data generating process. So ultimately, I just want to emphasize it again, our decision rule, the forecast is in this setup, is a function of the data generating process. Or sometimes it's a very simple moment, like average or median or quantile, and sometimes it's a more complicated object like here. But under certain assumptions, this can be further simplified. And so this is the next slide. For example, suppose that y's are independent, so there is no time series component. So it's like we're dealing with cross-section and y's are arriving independently from normal with mean mu and variance sigma squared. So ind means independent. Then we can calculate exactly this object, which would be by the this is its definition, and then using some simple algebra, we can derive that it's equal to this. And so that implies that ultimately our decision rule depends on mean and variance of the data generating process, if our assumption about the data generating process is correct. And so again, the mean and variance are features of the data generating process. And then here where the second step comes. So we're here dealing with the second step. We can then use any estimates of the mean. We can use any estimates of the mean and variance. For example, we can take an average and for the mean and this estimate for the variance. And this is where the second step, this is, we come up with the optimal decision rule in the population, and mu and sigma squared are population parameters of the data generating process, or parameters of the data generating process. And then we can bring estimates of the parameter of these parameters from somewhere else, some say consistent estimates. And that will be our second step. And once given the consistent estimates, we are done. Oops, sorry.
Could you please repeat the last idea about consistent estimates, especially from where we take them?
Yeah, actually, it's a whole big issue. So you understand up on this point, right?
Yes.
And then at the end of the day, we don't know these parameters. We need to estimate them somehow. We just assume that the data generating process is this. So it's normal up to unknown parameters. But then we need to estimate the parameters. Once we have the estimated parameters, we are done. We can do the forecast. But where do we get the estimated parameters? And this is how should I say it? It's tricky issue here. Ideally, you want as your sample becomes larger and larger, you want to do the optimal forecast close to the population, the forecast that you would do given the population, which requires that you should use some estimates of this, some consistent estimates of these parameters. Maybe unbiased, maybe biased. But you need to come up with some estimate of these parameters so that then you can have your forecast. Does this part make sense? Yeah.
Yeah, it does. So the question is just how to estimate them, right?
Yeah, how to estimate them, yes. And here, the issue is we we can just come up with, potentially there are many ways to estimate mean or many ways to estimate variance. Some of the ways are good, some of the ways are bad. And given this setup, there is potentially nothing that tells us which estimates of the parameters we should use. Or rather, many people, when they approach this problem of forecasting, they often don't think where to get the parameters. While it's like its own non-trivial question, how to get the best parameters estimates given your first step. I might be saying something confusing, or maybe not expressing myself clearly. Let me go back to the sample analog approach. In the sample analog approach, everything we did was based on the loss function. And we kind of, if you think about it, we kind of did these two steps together. We kind of, you can consider that example with a Linux loss function under the assumption of the y's coming independently from a normal mu sigma squared distribution. And then you can calculate under Linux function, you can calculate your decision rule from the sample analog approach. And then you can see what would be the implied estimates of mu and sigma squared under this sample analog approach. You can do that. And the important point here is that you will use both the same loss function to come up with the decision rule and for the estimates of mu square and sigma. Oh, sorry, mu and sigma squared. While in the two-step approach, you kind of separate these two stages. You calculate the dependence, how the decision rule works in the population, and then you estimate the required moments of the population distribution. And these estimates potentially can come from a different place, from some other loss function, from whatever. And this adds some flexibility, but this might be an issue. This might impact the quality of your forecast. But the point is that many people implicitly do this. They do the two-step approach. Okay, does it make clearer?
So again, many people use two-step approach, but they don't think about where they get in their parameters. Doesn't that mean that they are just using like a simple analog approach? No.
No, so that's the point. And this was, I think that was the contribution of Elliot and Timmerman, not in the book, but there as the researchers on forecasting. They pointed out this inconsistency between, so many people, they in effect were doing a two-step approach. Like, for example, if you're doing a quantile estimation, you would and to do then forecasting with the lean loss function, you would no, let me even the simple mean squared error. You on the population, you would need the average value, the expected value of y as your decision rule, and then in the second step you would use some estimate of the expected value of y. And it were Elliot and Timmerman that pointed out that actually you should be, and sorry, and then people would use, sometimes they would use an estimate for the needed parameters that are coming from a different loss function. And that was Elliot and Timmerman who pointed out that inconsistency by saying, look, you should be doing everything in the like with the same loss function. Like for example, let me go here with this example. Like for example, this estimate of sigma squared, if you do it with it's not the one that's coming out from it's not the estimate of the variance. There are many estimates of the variance. Here is another estimate of the variance. The difference is that here is t minus 1, here is t. And you can actually subtract any number here. You can subtract t minus k. And it also will be an estimate, and it will be consistent, but if k is not equal to 1, then it will be biased. The thing is that if you want giving your sample of y's, the quadratic loss, the estimate that gives the minimization of quadratic loss is this. This estimate comes from some adjusted quadratic loss, but I'm not sure that if you want to estimate the variance of the sample using this Linux laws, then you would get the same sigma squared. It's actually a good exercise. I should give you it as an exercise. Which sigma squared estimate would correspond to the Linux laws? But it can be something different. Does this make sense?
Yes, it does. And so some researchers just took the estimates, well, of the variance from, I don't know, another loss function just because it's easier.
Yeah, because it's easier,
Hmm.
right?
Okay, I see.
And because maybe they didn't think carefully, but I should say that now people understand this. In the forecasting literature, people understand this issue. But maybe in the past, people didn't think carefully about it. And so you derive this first step, okay, fine. It depends on mu and, not, sorry. You derive this first step, it depends on mu and sigma squared. Fine, then just substitute mu and sigma squared from somewhere. I think I have an example to work on in the tutorials about this. And you will see how it changes when you use a estimate that is consistent with the loss function and that is not consistent with the loss function. So hopefully, as we go along, it will be either on tutorials or in lectures. I forgot where I included this example. But as we go along, we'll see a bit more of it. All right.
And we should use the one consistent with loss function, right?
Ideally, but it depends on what you want to achieve. Actually, there is a paper that was published in I think Journals of Finance. I gave it last year in the class that I teach, the same class that I teach here at the University of Tokyo. I gave it as an assignment to replicate this paper, but it's a very, very hard paper to replicate. It's super hard. And the person who replicated became my student. I said, okay, you're the best. So the point is that I'm not going to give it anymore because it's a crazy hard paper. But the point of this paper is that they show that sometimes you can achieve a best forecast if you use different loss functions. They deal with the portfolio choice, like how you choose the assets in a portfolio, and then you minimize the variance that minimizes the risk, and then they show that the loss function that you use to estimate the variance of the portfolio can be different from the utility that you use to evaluate the income from your portfolio. And so your utility is your kind of high-level loss function, and how you estimate the variance of the portfolio, it's another problem. And you can use the same loss functions for the estimation of the variance of portfolio and for the utility, or you can use different. And they show that actually sometimes using a different loss function for the variance estimation gives a higher utility. So to reformulate it, using a loss function not consistent with, for the estimation of variance, not consistent with the utility, sometimes can be better. So to the question, you should use consistent, not consistent, it depends. But at least you should understand what you're doing. And what are the issues. And we will have more examples with this, and so hopefully it will be a bit more clear. Okay. I guess okay. So now a quick summary. So let me see. Yeah, a quick summary. So sample analog versus two-step approaches. The sample analog approach can always be used. We just formulate the sample analog, optimize. Two-step approach requires that the relevant feature of the data generating process is determined. The two-step approach is more ubiquitous in practice. And this is what Elliot Timmermans say why. This is not my opinion. This is their opinion. Why most people are doing the two-step approach. Because they think that up until some point, the majority of forecasting studies were using mean squared error loss, which was reducing the forecast analysis to attempts to estimate conditional mean. And so the whole forecasting estimation was about the conditional mean, not about the simultaneous choice of the decision rule and the estimates of the features of PYZ. Okay, that finishes this part. We're still in the realm of this classical approach. We will now consider a very important point, how you should interpret forecast optimality, what it even means to have an optimal forecast. This is also a very important issue to think about. And hopefully, by the end of this discussion, you will say, wow, hopefully. Because when I first saw it, I was like, wow, I never thought about it. So I think this is also a unique feature of this Elliott and Timmerman book where they talk about it. Okay, so one point that I already talked about is that optimal point forecast, just predict the outcome, aims to work well on average, given some loss function, rather than for a particular value single draw of the outcome. So in this sense, the forecast attempts to estimate not the outcomes wise, but a function of wise conditional distribution. I already talked about it at length when I was talking about the quadratic loss function. So let us go through, I have 4 observations about forecast optimality. Observation number 1, we should be making a distinction, when we're talking about forecast quality, we should be making a distinction between statistically good and economically good forecasts. Or if you want to go beyond the economics, we should be talking about statistically good predictions and useful predictions, I guess. So the useful predictions are the predictions that give the value, I guess, just intuitively, that give a value of the outcome that is not far away from the realized value ex post. I think this is what all of us think about when we think about forecasts and like how good they are. We usually think about how good they are in terms of how useful they are. If we hit the outcome clause or not. Say if the IMF predicts that the growth rate, so the current prediction of IMF in March of the growth rate of Russian GDP was something like -10%. Now their prediction is -3%. So turns out that -10% was economically bad forecast. Then because it was far away from the realized growth. But we can say that perhaps if we look back at the history of IMF forecasts of Russian GDP, maybe perhaps on average they do a good job according to some loss function. And so this is and that forecast of -10 may not be a reason to criticize IMF, because on average they do a good job. But sometimes they do a bad forecast because it's just it can realize. So I think this practical forecasting is a fine balance between producing statistically good forecasts and economically good forecasts. And for example, I talked a month ago, so IMF released their World Outlook report months ago, and I talked with the managers of the team that were working on the release of that outlook, and they were explaining me how they were constructing the forecast for the next year. And they were saying that they use a variety of methods. They use their own like general equilibrium economic models that solve some equations. They also use some statistical methods like what we are studying here. And also a super important input into their forecasts, interviews with all kinds of people, all kinds of ministers, businessmen, and economists, and hearing their opinion and thinking about all kinds of shocks that can arise, all kinds of alternative scenarios. And it all somehow then they combine into one number, which would be their headline number, and then some distribution around this number. And the point is that the statistically good forecast is only a part of their forecast. And these interviews with economists, businessmen, policymakers, this is the part where they're trying to make their forecast useful, where the economically good forecast. So there is statistical, which is the statistical model does, but then they correct it with the interviews to make it economically useful. Okay, hopefully that distinction makes sense. Clear?
Yes.
Okay.
Excuse me.
Yes?
Isn't it time for a break?
Yeah, okay. Yeah, so how long do we have? What is our break? So it's wait, sorry, I should have made the break at 4:50. Sorry. So we make a 20-minute break, right?
Yes.
Okay, so let's reconvene at let's say so what time? 11:45.
Okay.
Let's continue. So hopefully this point is clear. Statistically good, but not necessarily economically good forecast and the distinction between them. The next point is that
Excuse me.
yes.
We can clearly hear you, see the slide, but for some reason we don't see you.
Okay.
Thanks.
Sorry, I forgot to turn on the video. So the next point is we could potentially choose different sets of variables z. If you think about, say, a problem of forecasting income based on experience, education, age, and so on, you can have so many different variables in Z, like your neighborhood, the city where you live, the number of children, income of your spouse, and so on. And it can be just so many variants. Then when we are talking about forecast optimality, we can only talk about optimality for a particular forecast, for a particular set of z's, the data. The point here is that, of course, you can be comparing different models and choosing different subsets of variables to base your predictions on. But for each subset of z's, there is its own optimal forecast. And so by varying z's, you're arriving at different optimal forecasts for different z's. Now, another point, observation 3, is that, so we saw that the optimal point forecast were parameters of the conditional distribution py, the data generating process that we don't know, and then with MSE loss, the squared error loss, it was conditional mean. With, say, mean absolute average, it would be conditional median. That the mean absolute average is one example. Sorry, mean absolute error. Mean absolute error. I'm getting tired. So mean absolute error is the conditional mean, and the mean absolute error is a particular example of Lin-Lean loss. And then in this sense, the forecast unique in the population. But there are many estimators of any parameter of the distribution. And so we saw that I showed you that we can have different estimates for the variance in the case of that is needed for the case of Linux loss. And so in that sense, there is no unique, ultimately, there is no unique optimal forecast, because any forecast will depend on these features of the distribution that we need to estimate. The estimates are different. And so on the population, unique optimal forecast, but at the end of the day, we deal with our sample. And how would we define? There is no way to define optimal, or maybe there is for our sample, but there is no optimality in the sense of corresponding to the unique population forecast. Okay, then another observation is that we need to restrict the set of the models that we are using for the forecast. So here, if we go back to the formulation of the problem, I was using this minimization over some set of models, F, curly F. So obviously, this cannot be just some randomly large set of models. We are restricting ourselves within a particular class of models parametrized by some parameters, say. So that means that we are not even searching across all possible models, because otherwise it can be infeasible. And then once we start limiting ourselves to so this is this bullet, once we start limiting ourselves to particular models, particular parametric models, the optimal model that would deliver minimized risk might not be in that class. But searching for the right class can be a whole big problem that we might not be able to solve. Then suppose that we restrict this class of models in parametric form as a function of unknown parameters beta and data z, then we will be searching for across some parameters over this class F. So we'll be choosing right parameters, but then even this problem may not be unique. The solution of this problem might not be unique because of non-convexities. So that also brings that the implies that there is might not be a unique optimal forecast. And this point, I already made this point. This is basically if we make parametric restriction, but then at the end of the day, we need to estimate this parameter, which would depend on the data generating process, parameters of the data generating process. And then the expected loss will still be a function of theta, and then and some features of the data generating process. And then once we estimate the features of the data generating process, the optimal forecast is a non-unique. So it's like non-uniqueness is everywhere. And that just hopefully makes you realize that when we talk about optimal forecast, it's a very tricky thing. There's no such thing. Well, there might be no unique optimal forecast. And what you're arriving at perhaps is not the optimal forecast, but some good forecast, statistically good forecast. Even if you made all the assumptions, even if you specified everything very formally, you might never achieve the unique optimal forecast. And knowledge of this might actually give you some freedom in your choices, because you know that at the end of the day, achieving optimality, unique optimal forecast is impossible. And so then you can experiment with different forecasts. That kind of unties your hands, frees your hands. Yeah, let me skip this example. I don't want to spend too much time. I want to move on a bit. So one more point about optimality of forecasts. Sorry, that I want to make later. Let me talk about this slide, and then I'll go back to the previous slide. So optimal forecast conditional on future variables. So this is something different. Often we're interested in conditional forecasts, forecasts of the output, sorry, not output, outcome, conditional on a specific future path of another random variable W. For example, here's an example where that can be relevant. Demand for houses of a construction firm can be conditioned on the future path of macroeconomic variables, interest rate, economic growth, inflation expectations, and microeconomic variables, competition in the sector, regulations, and so on. So, and then given, say, especially the macroeconomic variables, the interest rate, we will give different forecasts for the price of houses. So in that sense, the extending what we've done to conditioning on some other variables can be done mathematically. It's trivial, but in practice it's very difficult to implement, because we can have feedbacks from our forecast to the future path of some variables. For example, if we're in a central if we're in a central bank and we do inflation forecast, then that fits into the decisions of economic agents that we might take into account when we are doing our forecast. of inflation. And so there can be this loop, and then how to implement this in practice, how to estimate how our forecast of inflation changes the decisions of economic agents, and then based on the decisions, what should be our forecast. This is a circular problem, and it's very important, and the whole macro literature is kind of trying to deal with this. Not the whole, but some macro literature, and the central banks, they're trying to deal with this issue. Okay, now let me go back to this slide. So suppose we correctly specified the forecast model, and so this FZB given the data and some parameter, and it's parameterized by beta. So this is parameters of the model, forecast model, not the theta ones that are the parameters of the data generating process. So suppose that this model is equal to the correct feature of the data generating process. It has to be theta here. Then both sample analog and two-step approaches require that beta is estimated from the data, obviously. And so then the actual model is this one, where beta depends on z and theta. But then when we calculate the risk to estimate our model, we take the expectation over z. And so we get, so the risks calculation gets affected by estimation of beta. And then the additional randomness induced by this estimation of beta can increase risk. And we are going to consider an example in a second. And then that one implication of this, that the estimated forecast model will never obtain the optimality properties discussed previously. So it's not only there are different estimates of beta, it's they induce their own errors, estimation errors. And so even with different estimates of beta, we don't achieve the optimal minimum value of the risk because of the errors in the estimates of beta. But here's the point. When we consider the optimality of the forecast procedure, ideally, we can and should be taking into account the parameter estimation errors, which would imply that there is no single optimal procedure that minimizes risk for all possible values of theta. Let us go through the example, and then I reiterate these points. This is very important. So consider a very simple example where our data arrives again independently from normal mu sigma squared distribution. And so we just have a t observations of y. This is all we have. They come independently from the normal distribution. Then if we are considering quadratic loss, our population optimal forecast, we know it's the mean, so it would be mu. And then the risk is just the expectation over z, expectation over y. Here we should write yt plus 1. That's what it meant. Would be yt plus 1 minus mu squared plus the data generating process, which we know it's normal. dz dy t plus 1. So this will be our risk, which is just by the definition of the variance of y is sigma squared. Then in practice, we don't know mu or sigma squared. We need to estimate them. Then suppose that we use the average value to estimate mu. Then instead of this object, our risk is actually will be calculated like this. Squared. Now this guy has the normal distribution with mean mu and variance this, because it's an average across t-independent observations, which are normal variables, and so average of t normal variables is a normal distribution. Then the risk of this forecast, we can again do the trick with adding and subtracting mu, as we did with the quadratic loss when we were calculating the optimal loss. It will be equal to this, which is equal to this. So this is sigma squared, and this is sigma squared divided by t. And so the optimal forecast on the population is this. But the forecast that we use, which involves estimate of the mu, has this risk, which is strictly greater. So we don't even achieve the optimal forecast. Now, let us dwell on this example a bit more and do one trick to blow up your mind a bit.
I
yes?
have a question.
Yes.
What if we use the unbiased estimate of sigma square?
No, we are not using the estimate of sigma square here. You see, everything we need for this forecast with the quadratic loss. So the data arrives y from the normal distribution. What's our forecast on the quadratic loss? Our forecast is just the mean value of y. What is the mean value of y? Well, we don't know, but we just calculate the average y, as simple as it is. Here, I'm just calculating the risk, the theoretical risk, which this I don't know, but I don't need it for my forecast. Does this make sense?
A little bit.
So just, I think this is a very simple situation. Just imagine that I start throwing at you numbers from a normal distribution with mean mu and variance sigma squared. You know neither mu nor sigma squared. And then I tell you, give me a optimal forecast of the next value under a quadratic loss. Your optimal forecast will be a mu if you know it. If you don't know it, your optimal forecast will be the average value. And so that's all. You don't need to know the sigma squared, the variance, to calculate your optimal forecast. But now I can go and calculate the risk of this forecast, and it's going to be this. It's a theoretical risk, and in practice, of course, you don't know this, but I don't need it. I just want to compare this number to this number. That's all. Okay. So let me now do the following. Suppose for this mu, instead of instead of this guy, we use gamma multiplied by as our estimate of mean, where gamma belongs to 0, 1. Obviously, it's an inconsistent estimate of the mean. But let us see what would happen if we use this one. Let us substitute this as an estimate of the mean into the risk. So it's calculated here. We can calculate it here. After doing some simple algebra, you can do this algebra, I'm pretty sure, very quickly. So we just calculate the expectation yt plus 1 minus gamma average yt. Then again, doing the trick with mu. We get this thing just to check that if gamma is equal to 1, then this term will disappear, this will disappear, and we are back to here. But now suppose that we gamma is not equal to 1. So we are asking this question, can this be lower than sigma squared 1 plus t minus 1, the one from here? Can it be lower? You can then calculate. So let me quickly solve this inequality. So it would be sigma squared gamma squared minus 1 t minus 1 lower than 1 minus gamma squared mu squared, and then divide both sides on 1 minus gamma squared. So that would be like this. And so we get that then this can be rewritten as 1 plus gamma 1 plus gamma 1 minus gamma. And so we get that if mu let's see if this is supposed to be lower. 1 second. I forgot. It's not like this. Yeah, I collected it in the wrong order, like this. And then if that implies that if mu is in this range, or if this inequality holds, then we will achieve a lower risk than the sample mean. Wow. That's amazing. And we actually even have the optimal value of gamma, which we can just see what value of gamma minimizes this object. And it will be this. And then if mu is outside this range, if this inequality doesn't hold, then average YT has a lower risk. Very weird, it seems like. So let us go back to this. What we have done. We know what is the optimal forecast on the population. Okay, perfect. That's the under quadratic loss. The optimal forecast in the population is the mean. We don't know the value of the mean, we need to estimate it. When we estimate it, we introduce the error. We can manipulate our estimate so that we kind of shrink the error. This is what is happening. We shrink the error that ultimately implies a lower risk. And this is, so by multiplying this thing by gamma, we potentially can achieve a lower risk, which could potentially could make our forecast better in terms of the expected risk. So this is a demonstration of the problem with the two-step approach, where we disconnect the estimates of the parameters and the loss function and the risk. But this here, there are different sources of this disconnect. There are different sources of the problem with problems with this disconnect. One problem is that we might not be using the same loss function for the estimate of parameters, and then that would increase the risk. Another problem is that we're using a finite sample to estimate the parameters, so there is an error which increases the risk. And we can shrink that error by using a different estimate. And there is another lesson learned here, is that depending on the value of mu, which we don't know, there might be different optimal estimators for our mean, and then different risks and different forecasts. But on the other hand, some gammas are never optimal. Like gamma outside this region 0, 1 is never optimal. So some forecast procedures are dominated by other forecasts for every value of theta. Does this example make sense?
And this conclusion that the lower risk we can achieve, what does it mean exactly in our chain of thoughts?
Yeah, that means that on statistically we will get a better forecast. So remember, let us go to the slide number 1 or 2. Whole point of this classical method approach was to minimize risk. And what is the minimized risk? Is the expected value across the data and the outcome. And we see that we have to be careful when we're minimizing that risk. We have to be careful when we are constructing the optimal forecast. We have to take into account that optimal forecast can involve estimates of some parameters that introduce errors into the risk, and then that makes risk larger, and so we can do some manipulations to decrease the risk, and that would give us on average better forecast in terms of that objective.
Okay.
Isn't it a curious example?
It's just a little bit strange, like we can somehow manipulate our parameters to reduce the risk of our mm, forecast method. It's about it.
Yeah, but there is a larger implication here, which is that, say, in econometrics, what you've learned so far, you were concerned with consistently and in a consistent and unbiased way, estimating parameters, doing inference, and then discovering some causal relationships. And once you change the problem to forecasting, you think that you can apply lots of tools from econometrics, and this is true, but you have to be careful because it's not straightforward, and this is, I think, a bigger lesson, because this problem of doing the optimal forecast in some sense, which is minimizing a risk, has its own implications. And that example is one of the simplest ways to demonstrate it. Okay, hopefully that, and of course, it's just a simple example and it was made up, but it's kind of a running theme of whole forecasting or machine learning, if you will, literature. You don't necessarily need statistically significant estimates of some parameters or unbiased estimates of parameters. You should always focus on your objective, and your objective is to minimize expected loss or risk, and that comes first. I think there is this bigger message in this whole discussion. Then
So we don't strongly rely on some statistical properties like we do in usual econometrics. We just need to make a good forecast, and it means like not following the straightforward procedure, but trying to do some approach just to minimize the expected loss or risk, right?
Yes and no, I guess. Yes, this is what I said, and so you summarized what I said correctly. But I also want to say that it's not like you should throw away everything you know from econometrics and statistics and probability theory. You should throw away out of the window. Of course, it's all useful. For example, very often you're not only concerned about a point forecast, but a density forecast. You want to know some error band around your forecast. An error band of like, I don't know, if you're forecasting inflation and you say that actually with 90% probability, inflation can be 5 times higher than I predict, versus then that tells you something about your forecast. So, and then in order to be able to come up with this distribution of the different probabilities for different forecast values, you need to use statistical theory, the econometrics that you learned, specifically statistical theory that you learned in econometrics or elsewhere. But it should be, the point is that it should be subject to your ultimate goal of optimal forecasting in some sense, or good forecasting. Yes. And I also wanted to make a point that econometricians sometimes they don't like this machine learning literature because very often what comes out of it, it's either a black box or you don't know the statistical properties of it. And it's kind of related, but a separate issue. Once you start doing this kind of manipulations, you might lose a sense of statistical properties of your forecast and or why you have certain outcomes, why you're predicting certain outcomes. And or for example, you start losing an idea of what happens to your forecast as the sample size goes larger, like you lose some kind of like notion of consistency or unbiasedness. And some econometricians I heard, they very high profile econometricians, they are skeptical about such approaches and they don't like this for this reason, that once you start introducing this kind of manipulations, you start losing some properties and you're dealing with something that you are not sure about. What are the properties of this object? Like asymptotic properties specifically.
But does it really matter in the context of forecasting?
Yeah, and that's the reply. Does it really matter? That's the reply. If I keep coming up with a good forecast, then does it even matter? But then there would be like Friedrich Hayek, that one of the like the represent the head of the Austrian School of Economics in the second half of the 20th century. He would say all forecasts are bad, like they're useless. So Hayek was skeptical about forecasts. So the point is, and then again, some econometricians might be skeptical. They would say the world is inherently unpredictable. So what you're doing just from the start doesn't make any sense. And then I will tell you the reply that people make to it. The reply would be, hey, imagine a situation, I set on fire a building, an office building. I can predict with 100% probability what's going to happen. Everybody is going to run out of the building. So, most 90% of people are going to run out of this. At least 90% of people are going to run out of this building. So the point is that there is this dialogue going on between econometricians, people who do forecasts. Some people are skeptical that you can ever do forecasts. They say there are limitations. Okay, maybe like you can do text recognition, you can do self-driving cars, but maybe you cannot predict uncertain future with your economic forecasts. Then some people say, well, we can. Here's an example with this people running out of the building that is on fire. And I think my view on this is that why I'm doing this, I think that the world needs forecasts, one way or another. That's why we need to understand it. We need to do our best when we are trying to come up with forecasts. So for me, it's a viable subject to study. And important, of course. Okay, I see there's like 3 minutes left, so I definitely let me cover this one in the last couple of minutes. That would be enough. So instead of expected loss minimization, which we have been dealing with so far, we can consider the minimax forecasting rule, which would be choosing the smallest risk across all possible values for known parameters theta. And then we say that one forecast f1 is preferred to another forecast f2, if the supremum over all parameter values of this risk is for f1 is lower than for f2. So why we start talking about it? If we go back to here with this example, we saw that depending on the value of mu, there is no best forecast. But then at the end of the day, we need to come up with the forecast. We don't know true mu, and we need to come up with the best forecast as best as we can. So what do? We don't know mu. We need to make some decision. So one way to deal with this issue, and and once again, so there are, for different mu's, there are different forecasts that will be better. So there's this whole family. And so one way of dealing with this issue is to say that why don't we choose the one rule that across all parameters gives us the best outcome. So like formally here. So let me give a formula given by this rule. Let me give you an example with the mean squared error, going back to that example. So the risk under this rule would be this. We calculated it already. Now, gamma, for any gamma less than 1, this risk is unbounded as mu becomes large. So we don't know mu, and if we choose gamma not 1, then this risk can be potentially super large if we made a mistake, and we should have chosen gamma equal to 1. But then if we made a mistake and mu is super large, then for gamma equal to 1, the risk doesn't depend on mu. And so in that sense, in that case, the worst case scenario over whole range of mu's, if we choose gamma equal to 1, would be this, while if we choose gamma less than 1, then the worst case scenario will be infinite. Then in terms of the minimax rule, it's better to choose this, this as our rule. Now, but there are alternatives. We can potentially, let me see. Yeah, we can potentially, let me talk about this. Consider some more formal approach to decide between methods. We, for example, can assign some weighting function to different values of mu's, or more generally, different parameter values, and then choose the forecast method that minimizes this object. So we average risk over all relevant parameters. And then we can have direct comparisons, obviously, across different forecast methods, because that would be one number for all parameter values. Another approach would be, if we are reluctant to come up with some weighting scheme, some people sometimes do some Monte Carlo simulations to calculate average loss for different values of parameters and compare different competing forecasting models. And then you can choose the least bad approach. So this is an alternative. But basically, once we start talking about this weighting scheme, we naturally arrive to Bayesian estimation. And that's where we end today, and that's where we need to continue next time. So that is let me just say to finish this that the need to somehow come up with some scheme that works, some forecasting scheme that works across different parameter values naturally leads us to a Bayesian estimation. But conceptually, Bayesian estimation is also takes a different view on the nature of uncertainty. And we're going to talk about it next time. Okay?
So again, summing up, when should we like move to Bayesian methods? Facing what problem? Or,
When we should move to the Bayesian methods?
yeah.
You mean when you should use the classical approach, when you should use Bayesian approach?
Yes, kind of.
Yeah. If you're a hardcore frequentist, then you never use Bayesian approach. If you're hardcore Bayesian, you never use the classical approach. But what do you do practically, right? Practically, ultimately, the question is which method is simpler and which method would give you, I guess, better guidance in making decisions, better forecasts. And it depends. Bayesian methods, they don't come without a cost. You need to decide about your weighting function, which is prior in the Bayesian methods. And also, but on the other hand, you kind of need to decide on your prior in the frequentist approach, kind of, but not exactly. And another issue is that Bayesian approaches can be maybe perhaps computationally more challenging because you're doing an extra integral. But maybe they can be more precise because you're like ensuring yourself through the whole distribution of parameters. I mean, you're thinking about the whole distribution of potential parameters instead of just one parameter that you estimate from the data. And so there are these costs and benefits, and I guess ultimately you should try doing Bayesian estimation and try doing classical approach and see what works better in your particular application. And we will have one assignment where the benefits of the Bayesian approach will be clear. And I think if you will be working with like forecasting or machine learning, application of machine learning to economics, or even broader machine learning methods, Bayesian approaches are quite popular, and you might gain an experience and see from practice where best to apply them.
Well, what if you know a real functional form of some data generating process, and you have to bet money on the estimate of the parameters. What estimate would you bet on ultimately, by Bayesian or frequentist?
Yeah, I wouldn't pretend to be an expert on this. I'm myself learning it. It's not my research area. And I should say that I tried playing on the foreign exchange market, and I lost lots of money because I thought that I can outsmart it. So I don't have so far a successful record of predicting exchange rates. In particular, I didn't predict that the Japanese yen would depreciate so much so quickly in February and March. So that's just to say that I'm still learning and I'm not as experienced as I can be. And I think I would go with Bayesian probably, because that I feel like it makes more sense. Yeah.
Okay, thank you for your take.
You're welcome. Okay, so yeah, and there is a bad news. I don't know what's going to happen with tutorials on Saturday, because maybe you know Victoria Frolova refused, decided not to go with the seminars. Partially this is my guilt, because I didn't prepare her. What I'm teaching to you is very unknown to her, and she thought that it will be easy for her if I prepare all the materials in advance. But I didn't prepare all the materials in advance because there's more. Usually at the University of Tokyo, I teach a bit differently, and the assignments that I give are much harder than I should give to you. And then and my class is relatively small, and everybody, it's an elective, and anybody who comes, they are all very motivated to learn. So it's like a very different environment. And it's also geared towards PhD students and master students. So they're who are supposed to have taken like econometrics 5 times already in like bachelor masters. So I didn't prepare the lectures, the teaching tutorials in advance, and Victoria said it's too hard for her because she cannot do it, and we don't know what to do because I don't have the time to teach on Saturdays. I did it the first time last Saturday, but I have other commitments in the coming Saturdays. So I don't know what's going to happen, which is bad, unfortunately. But I guess we will figure something out. Yeah, that's I wanted to convey this information. So it's Tuesday today. It's not clear what's going to happen this Saturday. If I teach it, which is unlikely, then it has to be online. But then again, there will be like only 2 people, I guess. Then it kind of doesn't make sense. So that's it from me.
This is unfortunate.
Yeah.
I guess
Yeah.
I guess we can try to book some audience, like a room with computers. In this case, everybody who comes will be able to participate online. Something like that.
Yeah. The only problem is that who is going, I really don't have. I started preparing materials in advance now this week, so that whoever comes can use them. but I don't have the time to be on Saturdays, especially the next 3 Saturdays. I have conferences, I have some other commitments, which were like planned way in advance, even before I was contacted by Sergey Gelyevich to teach this class. Yeah, very sad. Nobody to teach.
Can you maybe recommend some supplementary online course or maybe some series of videos?
Yeah, by the way, so I mean, it's very hard for me to about online courses. I forgot. I should have said it during the first lecture. Just 1 second. So here's one link that you all should, one YouTube channel that I think one of the best for explaining basic concepts. He is amazing, George Starmer. He's a statistician, but he has amazing explanations of all the basic things. Then, of course, you should go on Coursera and take Andrew, I think Nguyen's, or how do you pronounce Andrew Ng, course on machine learning.
He's from the University of.
He's at Stanford, I think. Yeah. And there is even a Russian version of his course. Yeah, you definitely should. Amazing, somebody translated. You definitely should check his course, but it's basic and I'm teaching a bit different, more geared towards economics and time series and a bit more high level than what he is teaching. But you definitely should go through his course. I myself went through his course like in the past, I don't know, 10 years, 8 years ago. But he has several now. Maybe I should also look through his courses. And last but not the least, yeah, I'm trying to remember. So check this person. He is my former colleague at the University of Tokyo. Can you access Twitter? So let me give his website. Okay, here's the person, Michal Fabinger. He's running his own data science machine learning school. There are ways to sign up. So he offers the following deal. You sign up for this school. He teaches you. And then you make a deal to give him a certain percent of your salary for some time if you have a successful employment. If not, then not. If you default, okay, but then it's like, I guess he will stop deal. I mean, it's a tricky thing. I'm not sure he will accept people from Russia, even though he was accepting people from Russia. Yeah, he was accepting, right. Yeah, and it's all built on trust. You can go there and learn his classes from his lectures. And I think people say that it's high quality teaching. And he is my former colleague and very good friend. He's now in Romania. And I haven't taken his class, obviously, because he's my colleague, but students who went through his school say that it's amazing. And yeah, you can look into it, see. He teaches a lot of people from all over the world. I think he's better than me because that's his job. I do tons of things, and my main job is economics. He's better than me at machine learning and data science. Like he's a genius. He's like a world winner of physics Olympiad, and he has 2 PhDs in physics, quantum physics, and economics from Stanford and Harvard. He's a genius. So anyway, take a look. That may be the best way actually to learn. Okay.
Yeah, okay, thank you.
All right.
Thank you. Goodbye.
Bye.
Thank you. Goodbye.